Hi, in this video, we will see what is Classiq platform and then we will explore its web IDE to create some state preparation circuits like well state and GSZ state. So first thing is what is Classiq? So Classiq is a platform to create, analyze and execute quantum circuits at the scale. At scale means if there is small number of qubits and gates, then it's easy to manually create the circuit. But as number of qubits and gates increases, then it's become problematic. This is where Classiq comes in the picture and it helps you to create the circuit using high level models and optimize those circuits by using optimization parameters. So if we see the uh, higher level working of Classiq, so it works something like this. We specify what we want to do using high level model, and here we pass the constraints or optimization parameters, and then that when we synthesize the circuit, then it's fed to Classiq synthesis engine, and that engine prepares the circuit. And that circuit can be optimized for different quantum computing platforms also, like IBM or Azure or Amazon bracket. So we see that it not only creates optimized circuit, but it also helps to use single high level model for creation of circuits for different platform. So this is how Classiq works. And now let's see how we can interact with Classiq. So Classiq provide two ways to interact with it. First way is using Classiq Python SDK that we will see in upcoming videos. And second way is using Classiq Web IDE that we are going to just explore now. So to understand how Web IDE works, we will create well state circuit using IDE. And well state circuit is used to entangle two qubits. So we will see how we specify at high level that we want to create the circuit, and Classiq creates for us instead of we actually going and placing the head mod and C0 gate and creating the circuit. So I will go to Classiq platform and I'm already logged in. So I will go to synthesis tab, and here we can see list of built-in algorithms and state preparations. So I have selected custom, and we can see that here we can specify function and constants. So here I will select well state preparation, and that custom model got populated with some more data here. So instead of selecting from here, I can also manually type here. So if we see that we have this main function, and in this main function we are calling another function called well state preparation, and in function parameters we are passing what kind of well state we want. So there are four type of well states: phi plus, phi minus, and psi plus and psi minus. So here we are getting phi minus. Let's make it phi plus. And if you're wondering how do we know that this function exists, so we can go to documentation of Classiq, and we can go to user guide. Then we can go to built-in functions, and in built-in functions we have these types of functions: state preparation, arithmetic, oracles, Hamiltonian, and amplitude loading. So we need state preparation, and then we will select well state. So these are the state preparation circuits which are available. And if we go inside well state, then we can see the code also. And same function is also available via SDK that we will explore later on. So these are the parameters available for this function, and this is the exact name of function. Now I will click on this synthesize tab, synthesize button, and then synthesis engine will create the circuit for us. So we have circuit here, and in the left panel, we can see information regarding our circuit. So we can see that depth is 2. Depth means, we see, so depth means how many gates or level of gates are used. So we can see 2 level of gates are used. Bits mean how many qubits are there. So width is 2 here and depth is 2 here, and it shows count of gates. So h is 1, cx is 1, and more data we can see here. Yeah, for now that's sufficient. And we can see that the circuit got created. Instead of b specifying, we want hard mark for q0 and then c0 for q0 q1. Now we have this circuit, and we can execute it. So I will click on execute, and here we can see that Classiq provides these vendors, and I will just select Classiq, and here I will select simulator, and in simulators I will select AER simulator. So I am not going to use any actual quantum computer. I will just use I will not use actual quantum computer. I will use this AER simulator to run the job. In sorts, I have 2048 sorts, and I gave the name. Here we can specify timeout seconds and other configuration. For now, I will just run it. And here we have the results. In result, we can see that indeed this is the result of 5 plus state, where qubits are entangled to collapse in same state. So we can see that 50% of time it's collapsing at 0 0, and 50% of time it's collapsing at 1 1. And here we can even export this as JSON or CSV format. So that's how we can create Bell state. Now let's go and create some other basic state preparation circuits. So now I will create GHZ. So GHZ, it's already here. And if you want to see, you can also go to documentation. It's always good to refer documentation. So in documentation, we can see that we have GHZ state preparation circuit. This is the name of circuits, and it accepts parameter as number of qubits. So what GHZ state preparation circuit does is that Bell state entangles 2 qubit, and GHZ state entangles n number of qubits. So here if we select it, okay, I will just copy paste from here. So we are specifying that we want GHZ state preparation function, and we want to entangle 5 qubits. That's why we are passing 5. Let's make it 6, and let's run the circuit. So here we can see we have 6 qubits. Depth is 4, and width is 6, and we have 5 C0 gates and 1 H gate. So now all qubits are entangled. I will execute it, and same thing, I will select AER simulator and run it. So since we selected 6 qubits, we got result of 1 1 1 1 and 0 0 0 0 0, 6 zeros. So here if we zoom, then it says 0x4 means 4 zeros. Now let's make some other state preparation circuit. So we saw Bell state, GHZ state. Now let's see this uniform state preparation. So in uniform state preparation, instead of collapsing at 0 0 or 1 1, all outputs will have equal number of chances. So I will select uniform distribution state preparation, Let's make number of qubit as 3 and run the circuit. Here we can see this time no C not gate, all qubits are just uh, head mark gate is added to just all qubits, and that's it. I will execute it. Let's name it uniform distribution circuit. And this time we will have 2 power n outcomes. So since we selected 3, that's why we have 2 power 3 equals 8 outcomes, and ideally all should have equal probability, but we can see that they are almost close to each other, which is around 0.12. Now suppose we want to create a state preparation circuit where probability of each state is biased or it's not equal. As we can see, it's equal here. So for that, we can use this generic state preparation circuit or function. So if I show here, so this is a generic state preparation built-in function. So I will just copy it. We have 3 qubits here. I will just copy it and then explain here. So I will go back to synthesis tab and replace my code. Now if we see here, we have some more things got added here. So function name is state preparation, and as we saw that for 3 qubits we have 8 states or 8 outcomes. So here we are specifying probability of each outcome, and while giving this probability, one thing must be make sure is that sum of all these probabilities must be equals to 1. And then we are passing number of qubits, which even if we do not pass, I think it should automatically detect. Yeah, it will automatically detect by counting the number of probabilities. And then we are passing error metric, and here we are passing upper bound. This thing we will see after some time. In same video we will see what's the significance, but for now we can just understand that this is the upper bound of error. So maximum error which will be tolerated is this, and we want circuit to be optimized in such a way that there should not be more difference in these probabilities more than this 0.01. So this is quite precise also. Now let's synthesize the circuit. And here we go. Now we see this is not much big, but it's big enough to create by hand, like by adding gate by gate. So let's first just execute it, and then we will come to optimization part. So on execution of circuit on simulator, we can see that here we gave, suppose for this one, we gave probability of 0.3, 0.05 and 0.15. So yeah, it's close to 0.5, 15 and 0.3. So that's how we can do state preparation by specifying probability of each state or each outcome. Now I will go back to synthesis page, and again either I can again click on synthesis, or I can click on this quantum program tab, and here I can see the list of all similar to Visual Studio. I can see all the circuits which we created till now. So I will just go to last one and see. So now here we will again come back to the width and depth of the circuit. So here we can see the bits is 3 because number of qubits is 3. and depth. So depth bits we can think of as this horizontal one, this vertical one, and depth we can think of this, but this horizontal one. So again, width is vertical and depth is this horizontal one. And here we can see the number of gates. Now here if we see this width, this depth is quite big for such simple state preparation circuit. And reason behind this is that we had specified very precise upper bound for our error rate. Now if we try to reduce it and again synthesis the circuit, this time depth is reduced to just 6 and width is obviously it will be 3. So what I just wanted to show here is that by playing with error rate and these constants which we had not touched yet, but by playing with the error rate and constants we can optimize or increase or decrease the number of gates or qubits which are used in the circuit. Now benefit here is that we are just specifying this once, that I want to make this circuit, I want to make the state preparation circuit for this probability, and now we are free to play with these parameters, and synthesis engine will create as many as circuit we want until we find the circuit which meets our need. So here even we can select backend also, for which backend we want to optimize, and we can specify how many maximum bit we want, how many maximum depth we want, and even we can specify how many like we can specify maximum, suppose rg gate, how many maximum rg gate we want, and we can also specify we want to optimize based on width and depth. So these things we will explore further in upcoming videos. For now I will just conclude the video here, and what we understood in this Jupyter notebook or video. So what we understood is that how Classiq is a functional, how Classiq provides functional level approach or high level approach to create the circuits. And then we understood how to create the state preparation circuits using Wave IDE. And then we saw how to play with optimization parameters and error rates to increase or decrease the depth of circuit. So yeah, thanks.